Extraction of metals. Metallurgy constitutes the scientific and technological process used for separating metals from their ore. Ores are naturally occurring materials from which metals can be extracted profitably. Elements may occur either in the free, or pure or natural state, or as part of a compound. Most metals, except for the unreactive ones such as copper, gold, and platinum, occur as compounds known as minerals. Minerals are the naturally occurring chemical substances in the Earth's crust and are obtained by mining. In reduction reactions, a substance loses oxygen. In oxidation reactions, a substance gains oxygen. Reduction reactions are key in converting metal oxides that are found in ores to metals. To convert ores into pure metals, energy must be put into the reduction reaction. Corrosion reactions, which are oxidation, turn the metal back into its more stable oxide form by adding oxygen, and energy is released in the formation of the corrosion products. Copper 2 oxide is reduced when hydrogen gas is passed over it. Copper 2 oxide plus hydrogen gas yields metallic copper and water. Iron 3 oxide is reduced in the major reaction that forms iron metal. Iron 3 oxide plus carbon monoxide yields iron plus carbon dioxide. Oxidation is the opposite of reduction, where copper metal reacts with oxygen and water to form copper 2 oxide, also known as patina, and iron reacts with oxygen and water to form iron oxide, rust. Rust, or corrosion, is the deterioration of a substance due to chemical reactions with the environment. The corrosion of a material depends on the physical and chemical properties of the material as well as its environment. There are several different methods of chemical reduction depending on the reducing agent. If you have carbon as a reducing agent, carbon in the form of coke, coal, or charcoal reduces many metal oxides into the respective metals. So we have tin oxide plus carbon results in tin and carbon monoxide, then zinc oxide, iron oxide, and iron oxide. Different numbers in here. Hydrogen as a reducing agent. Because of hydrogen's flammable nature, it is used in very few cases. So the reaction would be MO3 plus 3H2 yields M plus 3H2O. Now M stands in for tungsten, whose chemical symbol is W, or molybdenum, whose chemical symbol is Mo. Calcium is one of the most abundant elements in the Earth's crust and is found in ores. The most common ores are calcite, which is calcium carbonate, and gypsum. Calcium is separated from its ores through the electrolytic refining process known as electrolysis. This process uses electricity to separate the ores into their component ions. Positive calcium ions are attracted to a negative electrode. The ions pick up electrons and then become pure calcium metal. Magnesium is found in magnesite and dolomite ores. The ores are crushed, heated, and mixed with seawater. The magnesium hydroxide in the ores falls to the bottom of the tank. They react with the chlorine in the water, producing magnesium chloride. Electrolysis is the final step where magnesium metal is formed and it floats to the top of the tank. A second process, not as efficient, is when calcined dolomite ore and ferrosilicon are heated together, reacting to form magnesium metal. The main zinc ores are sphalerite, which is zinc sulfide here, zincite, zinc oxide, franklinite, calamine, and smithstone. Zinc metal is extracted from its ores via two smelting processes. And a little note here. Smelting will be discussed in more detail with the next element, iron. The ore is roasted, which means it's heated to a temperature slightly below the melting point in the presence of excess air to remove the sulfur and other impurities. Then, a dilute sulfuric acid solution is used to leach the zinc out of its oxides. A strong sulfuric acid solution is then used to leach more impurities. Zinc dust and steam removes other metallic impurities. Electrolysis is used to collect the zinc on electrodes using electricity. Zinc is alloyed with copper to form brass. Alloys will be discussed in the next topic. Steel and iron are covered with a zinc barrier coating that is applied by dipping the steel in molten zinc. This provides a physical barrier between the environment and the steel, protecting it from corrosion. After they are coated with zinc, they are known as galvanized steel and galvanized iron. The most common ores of iron are made up of various forms of iron oxides, carbonates, and sulfides. Hematite, also known as iron 3 oxide or ferric oxide, that's an old term, the main ore that is used to produce iron metal. Magnetite, the most magnetic of all iron ores. Limonite, siderite, and iron pyrites. The process of iron extraction from its ore involves the following steps. Concentration. The ore is broken down into small pieces, and clay, sand, and other surface impurities are removed by washing. Roasting. The ore is heated to a very high temperature in the presence of oxygen or air to remove moisture and carbon dioxide and to turn sulfur and arsenic, if they're present, into their oxide form. Sintering. If powdery, the ore is melted to hold the ore together. And finally, smelting. It is carried out in a blast furnace, which is a tall steel vessel lined with fire bricks. And now a brief description of smelting. The sintered ore is mixed with limestone, which is mostly calcium carbonate, and coke, coal that has been heated in the absence of air, and is introduced into the blast furnace from the top to convert the iron ore to iron metal. And here's some samples of coke. Preheated air at 1,126 degrees Celsius is passed into a blast furnace from the bottom, like this. There are different heating zones in the furnace where a variety of chemical reactions occur during the treatment. As the hot air rises up through the furnace, different forms of iron are made due to the many chemical reactions. Carbon monoxide that results from the combustion of the coke changes iron oxides into different forms of iron depending on where they leave the blast furnace. For example, down here you get slag and pig iron. Up here you get iron ore, and then you have various other products that are coming out. The three forms of iron that are used widely are cast iron, which is 3 to 5% carbon, wrought iron, 0.2 to 0.5% carbon, and finally steel, which is 0.1 to 1.5% carbon. They differ in properties due to their carbon and phosphorus content. Cast iron, also known as pig iron. The molten iron tapped off at the bottom of the furnace is solidified into blocks. This form of iron contains about 3 to 5% carbon and varying amounts of the elements manganese, silicon, sulfur, and phosphorus. These impurities makes the iron hard and brittle. It cannot be forged or welded by hammering. When melted, cast iron solidifies, expanding slightly. It is used extensively in casting toys, radiators, pipes, and agricultural implements. Wrought iron, a comparatively pure form of iron, is produced when cast iron is refined by oxidizing with hematite. Wrought iron contains 0.2% to 0.5% carbon and traces of phosphorus and silicon. This form of iron is ductile, soft, and malleable. The phosphorus and silicon impurities make it tough and resistant to corrosion. Wrought iron is used to make magnets in cranes and dynamos. It is also used to make chains, anchors, bolts, nails, railway couplings, and ornamental gates. Due to its relatively low reactivity, copper occurs as pure copper and in several ores. The principal ores are copper glance, copper pyrites, cuprite, and malachite. Copper oxides and sulfides are first mined, transported, and crushed. Copper oxides are then subjected to a spray of sulfuric acid, which dissolves the copper from the copper oxide ore. A type of electrolysis then processes the copper to 99.99% copper. Copper sulfides are heated to high temperatures, up to 1,260 degrees Celsius, then cooled and also subjected to electrolysis, producing 99.99% pure copper. Copper has been one of the metals that have been used to make coins, along with silver and gold, where copper coins were less valuable than silver and gold. Copper has risen in price over the last few decades, and copper coins have been replaced by copper-plated zinc coins. Copper conducts both heat and electricity very well, and as it is very ductile, it is drawn into wires for home and business wiring. It also has uses in motors, plumbing, cooking utensils, and roofing. Aluminium is less reactive than the alkali and alkaline earth metals, but still reacts with oxygen to form a layer of oxide that prevents further oxidation of the metal. Aluminium is a soft, light, silvery metal with a melting point of 933 K. In nature, aluminium does not occur in its free state. In the combined form, it is the third most abundant element. Aluminium is extracted from bauxite via electrolysis. It is malleable and ductile and a good conductor of heat and electricity. The important aluminium ores are bauxite, corundum, diaspore, feldspar, kaolin or china clay, mica, cryolite, and aluminite or alum stone. Because aluminium is resistant to corrosion, it is used in making cooking utensils and picture frames. It has a very high strength per weight ratio, so it is also used for aircraft bodies. It is used for making electrical transmission cables. In the form of aluminium foil, it is used for wrapping various food items, household and consumer products. Aluminium powder is used in flash bulbs for indoor photography. Mixed with linseed oil, it is also used in silvery paints. It is used as insulating materials and as a mirror in reflecting telescopes. Aluminium is very malleable, strong for its weight, and a good conductor of electricity. Copper is ductile, malleable, and an excellent conductor of electricity and heat, but is more expensive than aluminium. Because of its lower cost, aluminium was used for a time as household wiring, but aluminium oxide would form between the wiring and the copper wire from the power company. This would cause a gap in the circuit wiring, causing sparks to move between the two wires that could start fires in the house insulation. Building codes now prohibit aluminium wiring in houses.